the recording button. Oh, there we got it. Perfect, perfect, perfect. Arun, you want to say something first?
Oh, heavens, one word is all. So I just want to welcome Gregory and welcome everybody else. I'm just very much looking forward to hearing Gregory's thoughts. I think even though he has been here just for a year or so, he's clearly lightened up this whole area of relationships between COS and COE. So thank you, Hazel. Please go ahead to introduce Gregory more appropriately.
Great, Arun, thanks so much. Well, welcome again, everybody. And I'm so glad. It's a pleasure and an honor to have Gregory Abowd, who is both Dean of the College of Engineering and Professor of Electrical and Computer Engineering here at Northeastern University as our speaker today. I know Gregory as a co-dean, but in fact, looking through his bio, there's some really interesting things that make him well qualified to give today's talk and to help lead this very interesting exploration of the Internet of Materials. Gregory joined Northeastern not quite a year ago, and he came to us from Georgia Tech, where he was involved in something called interactive computing. His field, indeed, is human computing, human-computer interactions. He has been really a pioneer in the aspects of human-computer interaction and something called ubiquitous computing. And the work that he's done has had a great set of innovations, including addressing aspects of autism and technology, health systems, and computational materials. His background is very eminent. He received his Bachelor of Science in Mathematics from Notre Dame. And then as a Rhodes Scholar, I didn't know that until I read your bio today, Gregory, as a Rhodes Scholar, he got his MS and his MSc and Doctor of Philosophy from the University of Oxford in computation, and then went on to be a postdoc, a research associate at the University of York in England. He joined Carnegie Mellon as a postdoctoral associate, and I believe from there he went on to Georgia Tech, where he has, as I noted, had an illustrious career, and we were so fortunate to attract him here to Northeastern, both as Dean of Engineering and as a scholar in his field. So today he is going to talk about the exciting aspect of the Internet of Materials and to promote, as we're all interested in doing, very close connections between the College of Science and the College of Engineering. So Gregory, with no further ado, please take it away.
Thank you, Hazel, and thank you, Arun. And thanks everyone for taking the time to listen to what I have to tell you about. I'm gonna talk a little bit about some research that I actually started when I was at Georgia Tech. The last 5 or 6 years I was there. And one of the reasons I was interested in coming to Northeastern is I saw an opportunity to grow that line of research. And part of that agenda is talking to colleagues in the College of Science to try to explain what the vision is and see how we might work together towards this vision. And there are already people that are doing things along that line. So to just give you a quick outline, what I want to do first is to talk a little bit about how we think about making computers and what are the advantages and disadvantages of our current decades-long mindset of how we manufacture computers. And then that will lead me to saying we need to think differently about how we make computers. And I'll introduce very quickly this idea of the Internet of Materials. But what's important are 3 dimensions that drive the production of computers that fall into this particular category. I'll give some examples from my own work that's at Georgia Tech and here at Northeastern, and some examples from other locations. And then I'll step back and hopefully we'll have an opportunity to discuss how this agenda might be advanced at Northeastern and how it overlaps with some other activities that are going on, like the quantum materials effort that Arun is leading in advanced manufacturing and low power device work that's being done in the College of Engineering and elsewhere. So how we think about making computers and the good and the bad of that. So many of you are familiar with Moore's law, which was an empirical finding first communicated in the mid-60s by Gordon Moore, where he said literally the number of transistors you can buy with $1 will double every 1 to 2 years. And this is going to be possible because of increasingly clever ways to manufacture integrated circuits at lower cost with more and more components. Colloquially, these kinds of statements are what we typically attribute to Moore's law. We see throughout the course of history the introduction of some new computing items. So in 2015, the iPhone 5 was introduced, and at the time it said it was 2.7 times the processing power of the 1985 Cray 2 supercomputer, which in 1985 was the most powerful computer on the planet, right? And we become we see these kinds of statements so frequently that we're numb to what it's actually saying. But in the course of 30 years, we can see the progress that Moore's law and increasingly clever ways to manufacture integrated circuits results in things that we can have for cheaper costs, smaller size, and more powerful. And we're used to this. Another way to view this, and this is a graph courtesy of my colleague at Georgia Tech, Mike Filler, showing this progress on a different kind of scale. So if we look at how much it costs, how many dollars you spend to produce a mole, and I don't have to tell scientists the unit of measure of a mole, I have to tell computer scientists this, but not folks in the College of Science. This is a graph that shows this trajectory of Moore's law from the mid-60s to present day. And you can see that dramatic drop, 6 orders of magnitude in the drop of the cost of that amount of transistors. So the progress has been staggering. And as a result, we've seen in many different domains, and here are 4 different examples in the upper right-hand corner, looking at personal portable computers and how they have advanced in the span of about 20 to 30 years. We see the same kind of progress with mobile telephony in the bottom right-hand corner. The upper right-hand corner is looking at augmented reality and initial examples of augmented reality with lots of bulky equipment on an individual, all the way down to 20, 30 years later, it's sitting on a handheld device. Same kinds of progress we see with virtual reality. So Moore's law has delivered to us the ability to assume that technologies that might be bulky and clunky and not run in real time today, without any additional progress on the application itself or that technology itself, Moore's law will automatically create hardware that those applications will run more effectively and efficiently and smaller form factor at a lower price. So this is great. In addition to that, my area of research in ubiquitous computing was profoundly influenced by the writings of Mark Weiser. This particular quote here from a Scientific American article written in 1991 was in many ways influenced by the progress of Moore's law and the fact that we could start to see smaller and more mobile and functional laptop computers by the late 80s. And Weiser envisioned that this would mean even more variety. He said, extending that out, he said this would mean that the computer as a technology might become so profound that it would disappear. And what he meant was that it would no longer be so obvious what's a computer in our everyday environment because there would be so many of them and they would take on many different shapes and sizes to the point where they would be indistinguishable from our normal everyday life. And he introduced this idea of different scales of technologies. He took the analogy of an inch, foot, and a yard, saying there are some inch scale technologies that would be on or around our body, and we'd have many of them. Things like smartphones that came about 20 years later. Foot scale things that would be like the tablet computers that we have today, and yard scale devices that are like large scale displays and electronic whiteboards, all things that we now take for granted. He predicted in the late 80s that would happen. And a lot of that was influenced by just assuming Moore's law was going to move forward and we could start to be more creative in the kinds of computing devices that we would bring into our everyday lives. On top of that, we all know that our world is very much fueled by an unending thirst to use data to help us better understand how things in our world work. So we can see lots of different kinds of data mining applications. Just a few of them are listed here. But we have an insatiable need to get more and more data and to reason about that data so that we can predict and avert catastrophe or make predictions in medicine or in whatever kind of category. So in addition to having many different kinds of computational devices that would be spread throughout our world, small ones that might be doing sensing, all the way to very large one that could do large number crunching, we see the value of this in pushing forward our data-powered world. So that's the good news. Now the not so good news. I said that Moore's law has shown a dramatic decrease in the price of transistors, but relative to other things that we manufacture, computers are actually pretty expensive. So if we look at these other kinds of molecules or things that are mass manufactured, they're produced in that quantity of a mole far more cheaply than transistors. And part of the reason is because transistors are manufactured using a fully integrated manufacturing technique, whereas these other compounds use a different approach, a bulk or modular manufacturing approach. So we might think that we shouldn't just stick to fully integrated manufacturing to drive down the cost of these transistors or computational elements. So cost is one problem. Another problem is that, very unfortunately, most of the computing devices that we build and sell and have with us don't stick around very long, and they're not very favorable in terms of the way they decompose or degrade over time. So electronic waste or e-waste is very unfortunately the fastest growing waste stream that we have in our world today. So cost and waste are problems. In addition, power is a challenge. I find this very interesting that today, data centers, big data centers around the world consume about 1% of all global electricity, but within a few short years, they're envisioned to consume 20% of the world's power supply. That's a meteoric growth, and that's very concerning. That's power that could be otherwise used for other purposes, or power that wouldn't need to be used and wouldn't need to consume the resources needed for that power. So the conclusion is that our reliance on what I'll call ubiquitous computing is only going to grow. We don't seem to have an end to our appetite to be able to sense and compute and reason and understand things about our world and provide services to individuals. How we manufacture these computing objects that provide ubiquitous computing literally threatens the planet. It's too costly, it produces waste, and it consumes too much power. So because these two facts that I point here points to a collision course that may not be that far off into the future. And I think it demands that we think differently about how we make things that compute. And part and parcel to that is to think about how they're powered, what materials we use to produce those computational objects, and what are the processes that we use to do the manufacturing. So that ends the first part about setting the stage and the motivation for why we need to think differently about how we make computational objects. So I'll introduce this idea, the Internet of Materials, as a way to think differently about how we make things that compute. And it'll center around those 3 points I had on the previous slide, 3 factors that drive computing going forward. So a little bit on why I call this the Internet of Materials. Well, what I want to call this is the Internet of Things. But the problem is the Internet of Things has already been used. And in fact, that's a term that's been around since 1999. And if you do a search on the web, you'll get pictures like this that talk about the Internet of Things. But if you look at the items here, these are devices, computational devices. They're not what I would consider things. So the Internet of Things, as it's turned out, isn't really about things at all. This is a picture that shows examples of things in our everyday lives, some of which are computational, many of which are not. So what might this world be that I'm talking about? Well, I said, well, maybe think about this as an Internet of Materials, where the materials we use to make everyday objects can now be augmented with the ability to provide functional capabilities like we expect from some computational device. So there's three simultaneous challenges that are motivated in the previous part of this talk. Number one, we have to worry about how to power. If every material in our everyday lives has some computational capability, it's going to need power to do that. We need to think about what they look like and the materials that they're composed of, so we can think about their look and feel, whether they, as wiser motivated, whether they disappear into our everyday lives and we're no longer as obvious to us, but also if they're, when they go out of use, what happens with the waste or the end product, and what kinds of materials are used to manufacture them. Finally, we have to think about how costly it is to manufacture these things at scale. So with the simultaneous design challenge is to create things that are self-sustainable with respect to power. They are innovative with respect to the materials that are used to compose them, and they're cheap to produce in large quantities. So that's our simultaneous challenge. And the goal here is to do all of these things at the same time. Now, I'm going to try to show you some examples that aspire to get to these directions, but don't quite get there. And that's to seed some discussion about what we might do to take this agenda further with better and more expertise in particular areas, particularly in manufacturing and in material science. So this first example I'll talk about started about 4 or 5 years ago from one of my PhD students, Nivedita Arora, and a colleague, Thad Starner, in computer science, as well as a material scientist at Georgia Tech, ZL Wang. The idea here is to take an effect called triboelectric nanogeneration, which takes a property between two materials that generates a redistribution of charge and control it in such a way that what results is an alternating current or electricity. I'm going to show a quick video here of the ideas behind the simplicity of how you might produce this self-sustained vibrational sensor.
When sound reaches SATURN embedded into an object or surface, its structure microvibrates, resulting in both layers getting in contact, generating negative charges on PTFE and positive charges on the copper-coated paper.
So we have a material here that's a multi-layer material, has a number of different materials: paper, copper, a plastic, PTFE, and then another layer of copper.
As the layers separate, potential differences built over the two copper layers, causing a current to flow towards PTFE. The next vibration results in the layers getting closer and in contact again, resulting in a reverse direction of current flow that completes the cycle of electricity generation.
So that was a very short way of trying to describe how the fact that a redistribution of charges that occur naturally when two materials are brought close to each other and then separated, if controlled and providing a way to balance the electric field that happens when things are separated, you can produce an alternating current. And here the vibration is a sound wave. So you effectively encode the sound in the alternating current that results. And there's no power source that's needed for this to happen. The triboelectric nanogeneration effect takes the source signal, the sound wave, and converts it into the electrical wave. So this kind of self-sustaining sensor is an ideal opportunity to try to exploit. Taking this one step further, you need to be able to take the sensed signal, the electric signal that is representing the vibration, and you want to communicate it somewhere. And again, you want to do this from a device like the SATURN patch without requiring a battery or other power source on the material itself. So in this particular project, again, this was done by my student Nivedita and other colleagues, created a very simple, on the left-hand side, an extremely low power circuit that acts as an oscillator in the presence of a radio field. And this oscillator will backscatter or reflect the incoming radio signal and modulate it with information from the sensor that is attached to that circuit. And this simple video I have here on the right is just going to show you very quickly a variety of different sensing modalities, including voice, that can be attached to this circuit to provide this wireless, very extremely low power platform for doing wireless sensing.
We present MARS, multi-channel ambiently powered real-time sensing, a platform that enables creation of touch, swipe, and speech-based wireless sticker interfaces. Mars stickers consist of simple circuitry, have thin form factor, and consume nanowatts of power, allowing for ambiently powered battery-free operation. Just like a post-it note, Mars stickers can be attached to everyday surfaces to sense human interactions. For example, a conference brochure is an extended microphone, restaurant menu to order food, and a game controller.
There's a lot more detail on both these projects in the references that are cited at the bottom of the slide. I just want to give you a taste for what it means to try to build something that's self-sustaining, made from simple materials or simple circuitry, and has a form factor more like the form factor of everyday objects.
We present.
Second example I want to give you is going to look at the fact that if we can detect light patterns around various objects, we can understand something about how that object is moving and its relationship to other things in the world. This is work done by a former PhD student, Ding-Chen Zhang, and my collaborator, Kenneth Fuentes, who was at Georgia Tech and is now here in ECE at Northeastern, and Bernard Kiplin, who is at Georgia Tech. So in this particular work, we're looking at simple photodiodes. So the little bracelet at the top has 8 diodes arranged in a linear pattern. When wrapped around your wrist, it also has a solar material there to collect enough power to power the reading from the photodiodes, which are fairly low power in and of itself, but also to do some computation on that signal and to wirelessly communicate information off of that little band. When that band is placed around your wrist and you walk, your arm will move as you're walking. And that movement pattern, as you can see here in the video, can be detected to count steps. So effectively, this is a self-sustained activity sensor that can count the number of steps of the individual wearing it. Very simple example here. As I said, the photodiodes here are pretty low power, but the more you add, in this case, we have 8 in linear pattern, the more power that's needed to read the signal across all of those. Well, in some additional work that was done after this project, we showed in a project called Computational Photodetectors that you can arrange pairs of photodetectors in such a way that the power needed to read any number of them is constant. So it doesn't grow as the number of photodetectors in the particular arrangement. So on the left here, you have one that has 4 pairs of these photodetectors, and that particular arrangement can determine left-right movement or up-down movement across that particular pattern. And again, these are very low power. These don't really depend at all on what kind of photodetectors you use. A lot of the work that Kenneth does and Bernard do is in organic photodetectors. So being able to produce very thin film, low temperature manufacturing computational entities. So these can essentially be additively manufactured. The important point here is that you can create arbitrary patterns, and those patterns can communicate information. On this top video here, there's a computational photodetector on the shelf. And as you move something over it, you might not be able to see in the screen there, it's detecting that something moved over from the bottom and to the right. In this example, a box is being placed over and is then being moved off. So the shelf can detect the activity of things that are being placed on it. Add a computational photodetector onto the box itself, and the box can know that it was going over something and exiting a particular way. With enough of the pattern of that computational photodetector, you can communicate information beyond just movement. So I might want to identify a box or identify a shelf if I want to do something like inventory control. This bottom video is going to show you an example of this. This is done fairly slowly, just so you can see what's happening, but we have an array of these computational photodetectors that are set up like Braille. So if you rub your finger across them, you can read the Braille characters. But in addition, because they're these computational photodetectors, they can sense the movement of the finger over the pattern and can wirelessly communicate to the laptop just next to it what letters are being traversed while the finger goes across them. So I'll just show this real quickly. Again, this is slow so you can follow it.
T, E, C, H, tech.
And what's important there is that you didn't need much power at all, you have a little strip on the left-hand side of that braille strip that's collecting from the ambient light enough power to allow you to do the sensing, the computation, and the communication of that information wirelessly through a standard Bluetooth protocol to the laptop. So those are some examples of things we did at Georgia Tech over the last few years. And while I was here at Northeastern as well, trying to explore this idea of these computational materials. There are other examples elsewhere. I'm going to highlight two examples here by a group that's at Northwestern. This is work of Josiah Hester and his lab, where they showed how you can create a consumer electronics game, the Game Boy here, and power it with different kinds of sensors, like energy harvesters, like a little solar cell, or any buttons that use movement to generate the energy to read the fact that you press down on the button or not. And also using smart kind of computation, which they refer to as intermittent computing, which can do computing that seems like it's continuous in real time, even though the energy source is intermittent, so it can be interrupted at any particular point. A little more serious application of this, which came out just recently, and this was work that was a collaboration with the Northwestern lab and some folks at Georgia Tech, was saying, how might you take personal protective equipment and harvest energy from the fact that it is coupled to the human skin and breathing. If you remember from that SATURN work, how you can take vibration from voice, well, breathing is one source. And how can you power a mask that can actually do constant sensing as well to determine whether the fit of the mask is appropriate, to be able to determine rate of respiration. You could even think taking temperature along the skin or doing some kind of chemical analysis, but doing this in such a way that it is still mask-like and functions as a proper PPE should function. So there are lots of opportunities for looking at how you might embed self-sustained computing into everyday objects to provide lots of different opportunities. So I want to step back from those examples and say, what's the point here about thinking differently? Well, if you're influenced by Moore's law, then you have Moore's law thinking, which means you believe that computers are always going to get smaller, they're always going to get cheaper, and they're always going to get more powerful. Now, I'm not arguing one way or the other in this talk as to whether Moore's law will continue or has been holding true. That's not the point. What I'm saying is whether or not this is true, this kind of thinking leads you to believe, and you can see the evidence of how technology can evolve over time. And the key insight underlying Moore's law is that we will have more clever, integrated manufacturing techniques. I want to add to that another way of thinking about where computing might go. We might think that in the Internet of Materials way of thinking, that materials are always going to get more functional, meaning they'll be able to do more sensing, more computation, more store more information, communicate more. They're going to get cheaper, and they're going to be more sustainable. They'll be made from materials that are renewable. They will be biodegradable. They will have less harm on the planet. They'll be more power independent. And the key insight there is that to do this, we have to innovate on the materials that make up the computing objects and the way we manufacture them. So if you take on the bottom here, taking this Internet of Materials form of thinking and say, what might it be in years to come? We can take this kind of bulky brochure microphone that was shown in the video. It was printed, it said, onto the program at a conference, and you simply lifted it up and spoke, and it became your remote microphone. Well, it was a little bulky, what was there. You can see these regular integrated circuit elements there, the SATURN patch, a little solar collector, and an antenna. But if Internet of Material thinking is right, in some number of years, these will become like a Post-it note, only it'll have functional capabilities, like a Post-it note where if I touch that red button, I can speak to it and it'll transmit my message, or may do other functional things. Imagine the label on a bottle of Coca-Cola being able to recognize your voice and being able to personalize the label to you because of what you said, or being able to wake up something because you've spoken your name or a particular keyword. The OptoSense work with a little wristband that could do simple things like measure your step count. Imagine eventually with Internet of Materials thinking that we'll be able to embed that into something like a silicone rubber bracelet that is waterproof, very cheap, and oh, by the way, can do the same thing that a 3D accelerometer can do when mounted on your wrist, and do all the kinds of things that we expect with Fitbits and other kinds of health activity trackers. That's the direction that I think we should be thinking we will be getting to with this Internet of Materials thinking. So now I want to stop from there and just spend maybe 10 minutes talking a little bit about the opportunity here at Northeastern, which should give us a good maybe 15 minutes or so to have a discussion with everyone who's here about what you like about what you heard, what you don't like, what is confusing, and where are the opportunities for science to help advance this particular agenda. So I want to start by saying we have to broaden our perspective on how we think about computing and applications. So many people, including myself, who are trained in human-centered forms of computing, try to think about the people and the problems for whom a technology is trying to solve or introduce a new opportunity. But then once you want to realize that, you create applications that manifest that on some set of technology. And those technologies are running some algorithms that do the right kind of response to input and data that has been accumulated and stored. Those are run on some platforms that provide a certain number of reliable services like file storage and communication and computation. Those algorithms that represent the system operating system run on circuits that have amazing amount of complexity. Those circuits are made up of constituent devices that we can assemble together in known ways. But that's usually where we stop in terms of the stack of how we go from the computer all the way up to things that address opportunities in the world. What I've been arguing is that we need to also think about the way those devices are manufactured and the circuits put together, and even more so, the constituent materials that all of these things are built from. The problem today is that we start at the device. We're given these integrated circuits that already have properties in them that we can't change. They're already not biodegradable because of the way they've been manufactured and the materials being used. So if we want to overcome those problems, we have to get down into the fabrication techniques and the materials. The projects I showed you, the examples of computational materials, all benefited from expertise that cuts across every single one of these layers. And the only way you can do that is by broadening the mindset of individuals who work in this space to say, we need to think about people and problems and requirements understanding, all the way down to understanding constituent materials that make up the computing devices. And if that's too intimidating to a single individual, you at least have to admit that you want to be exposed to people with that kind of expertise. We can no longer just assume that we're given circuits and objects and we just create algorithms and applications. I hope I've convinced you that that's not enough for us going forward. So one thing that we can do is to look at innovations in the materials world to see how that might inspire different ways we can create a variety of computational objects or computational materials. So just some simple examples, some work that's being done in new forms of display technology, very low power, sprayable display technology, electrochromic, some work on how you might use wood or cellulose to harvest electricity from heat differential, or ways you might use protein nanowires to use moisture in the air and generate electricity, essentially create a patch that is a biodegradable energy source, a battery that grabs its energy from moisture in ambient room temperature. Some innovations I want to tell you about that are just within the College of Engineering at Northeastern I want to highlight. On the left here, Izong in Mechanical and Industrial Engineering has an amazing career of looking at how you can take certain kinds of materials like recycled paper and turn them into functional capabilities. In this case, a cooling material that is robust enough to be used as a roofing material to cool buildings with a renewable, recyclable material. Professor Zhang has several examples of how you can take recycled materials and turn them into functional materials with robust properties. Professor Hongli Zhu, also in mechanical and industrial engineering, has looked at how you might create biodegradable functional objects. Here, a water-soluble sensor that can be used. So we have a lot of expertise in the College of Engineering that already looks at how you can take materials that have interesting properties. They're non-toxic, they're biodegradable, they're made from renewable sources, and turn them into functional materials by the way you manufacture them. So these are tremendous advantages that we have here at Northeastern in exploring these kinds of opportunities. Within the College of Engineering over the last 6 to 8 months, my colleague Kenneth Fuentes has been leading a team, and many of them are actually on this call today, that's been looking at this opportunity of the Internet of Materials, and we meet weekly. If you are at all interested in presenting your work or in joining the discussions, please contact Kenneth or myself, and we'd be glad to bring you in on these discussions. I want to end here by talking about something that is particularly relevant in the context of Northeastern and our new academic plan. Part of the academic plan talks about having global impact in our research by being problem-driven. So what are the problems that this vision I've presented you may be addressing? And there are a number of them, and they're different kinds of problems. So I motivated all of this from a kind of sustainability argument, that the planet will not be able to survive our insatiable need for computing and the way we go about manufacturing computing today. So if that sustainability argument is what drives you, thinking about alternative ways to produce those functional computational capabilities can be the driving force here. And we already have expertise in mechanical engineering and a lot of the modeling work that's done in a variety of places in science and in computer science and in other parts of engineering, all about trying to understand, well, what is the sustainability argument for a different way of manufacturing these computational devices? It's one thing to say that self-sustaining from non-toxic renewable resources that are biodegradable in particular form factors. It's one thing to say that that's better for the planet, but it's another thing to prove it given knowledge of how the manufacturing materials are harvested and put together. You could also think about particular application domains where this notion of self-sustaining wireless sensing capabilities would be of value. And the two areas there are in thinking about our built world, whether it's the natural or the built infrastructure that makes up our cities. So smart infrastructure. And here, people in civil engineering know a lot about what it means to create infrastructure that supports an understanding and resilience of that infrastructure or predictive capabilities of particular structures, as well as marine and environmental science, which looks at coastal sustainability, for example. So it's not just about buildings, it can be about nature as well. So infrastructure that needs more sensing needs to have sensing that can be broadly deployed, cheaply deployed, be self-sustaining and robust. But we can also think about our human bodies and how we might improve our understanding of personal health. And people in Bouvet and in bioengineering are particularly interested here. And there's two angles to this. One is strictly the sensing opportunity. How might you deploy large-scale solutions for sensing on the body, either through objects that you place on your wrist, like a watch here, but do not have the power requirements, or the textiles that we put on our body to be able to understand something about human movement or physiology of the human body. But you can also think about biologically inspired ways to produce the computational phenomenon that I've shown. I haven't given you any examples of how we might look to biology, except for the work of Professor Zhu that I highlighted, using biological analogies and inspiration to show how we might reproduce things that nature does much more effectively and manufacture these efficient computational entities. So those are problems that can drive what we're doing. And obviously, to make any impact in these problems, we need to look at a lot of disciplines. And these disciplines, I'm only highlighting the kind of technically oriented disciplines here. There's plenty of non-technical disciplines here that can inform the work. But from the materials perspective, work we have in chemistry and chemical engineering, and in biology, and bioengineering, and physics, and material science, in particular, the Quantum Materials Institute and efforts that Arun has been talking about. These are all very interesting disciplines that help us understand what are properties of materials that can lead into this a world of the Internet of Materials. Once we have the materials, there's a very interesting synergistic relationship between materials you use and their properties and the way you go about manufacturing them and the processes involved. Those are things that are not entirely separated. We do a lot of work in advanced manufacturing, in mechanical engineering, and in electrical and computer engineering. And I'd love to learn more about advanced manufacturing efforts outside the College of Engineering. And finally, work in low power devices or self-sustaining devices. There's efforts in ECE through the Smart Center and the Wireless Internet of Things Institute, and also researchers in CORE looking at how you might produce very low power algorithms, either through quantum techniques or other techniques. This is all what I've presented here, this vision of the Internet of Materials. It's a fairly broad and bold vision, but it's also part of a larger discussion that I think we are having and need to have more of at Northeastern. How do we link topics like quantum materials, advanced manufacturing, and the low power device development that we have in various institutes and departments here? How do we bring all those together so that together they can accomplish something much more powerful and meaningful than they do just by themselves? And with that, I'm going to stop and just recap the main messages here. I hope I motivated you to think that there is an urgent need for us to think differently about how we manufacture computing, and how can the College of Science lead or contribute to this larger agenda. And I'm going to stop there, and we have a few minutes for discussions, and you can put your questions in the chat, or if you can turn on your microphone and just give me your feedback now. And if you don't want to do it right now, you can send me email or come to any of our weekly Internet of Materials discussions and join the conversation.